notes today. Thank you so much for powering through it with me last time. We are going to keep going. Before we get into that, though, the question for today is simply this. The launch area for the European Space Agency is not in Europe. It is in South America. Why?
Cheaper land.
No, this is not a joke.
Cheaper pricing per square foot.
Good guess, but no.
Labor costs. I'm guessing you don't have any before?
No, not today.
No, that test rate might be placement on
Say that again, Seth.
It's placement near the equator. Right? It's more it's geared towards the center, so it's something with trajectory I'm thinking of.
Yeah.
I don't remember what the actual
Term.
You're right on the money. Seth is right on the money. So here's the thing. Europe is up here. When the Earth spins, Europe is not spinning very fast when you consider the rest of the world. So up here, you don't have a very high tangential velocity or straight line velocity. But lots of places in South America do. Because South America, a lot of it is around the equator here. Specifically, actually I don't know exactly where their launch pad is, but right across the equator, you've got the northern part of South America, and this is the area where the European Space Agency has their launch pad. Because if you launch from the equator, you automatically launch with a starting velocity of whatever the rotation speed of the Earth is at that point. So you want to launch closer to the equator as possible because then it doesn't take as much fuel to get out into space and reach the speed you need in order to orbit the Earth. That's why they're there. So why is it there? Because you get basically free fuel by doing that. You're automatically moving faster. The worst place to launch would be from the North Pole or the South Pole because you have no tangential velocity from those points. You got to come up with fuel to get that extra velocity out from somewhere.
You gotta come up with that on your own. So.
That's why our launch area is in Florida down here as opposed to like New York up here. All right. Onward and upward. Pun intended. What we're going to talk about today.
Are we done? Actually found that? That's all we had time?
Yeah. You can title your notes for this section, Solid Object Under a Net Torque.
my head is
Oh my god.
just kill me. Just come out here. We had another test.
Under
I just
a
find I'm
net.
used to my test not going very well.
I'm sorry to hear
No,
that.
I was just so good on the review, and then the test is nothing like the review.
Did you end up doing okay on that one a while ago that you were really worried about? Oh, good. Well, you probably did just fine on this
You
one, too,
got
then.
100%.
Well, it's Sarah.
But I didn't get a 0, so I still got a B. I got a B, even though I got like so many different answers.
Nothing wrong with a B. I would have killed for a B in some of the math classes I took in college.
At this point, I'm just hoping for a B in calculus. But based off of this test,
Goodness, what was that?
was quite easy. And then we get to the-
What do you got in your backpack?
Well,
I
it's
suppose
water
not.
bottles are metal on the sides of it. So
Okay. As long as it's not that plutonium. What'd you say? Oh, physics book? Yeah, that'll do it.
You know, I'm gonna do it for you real quick.
Okay. So, solid object under a net torque. That's something that we talked a lot about last time. We talked about how that affects the forces on objects that are holding still. Today we're going to be talking more about what happens with objects that are not holding still. But believe it or not, this is not as hard as last time. So,
I don't believe it.
worry not, my friends.
I don't believe it.
So, overall, your torque is equal to radius times force. That should look familiar to you. Of course, you could also say it's equal to RMA. And if you want to get angular acceleration in the mix here, you could say Rm, and then acceleration is R alpha. Ra.
Jesus fish.
Right.
Do you have to do anything
But
tomorrow?
doesn't that then send the R
I'll
squared?
tomorrow is just going to be something really short.
Radius times itself.
Wouldn't it then send the R squared and alpha?
I'm glad you brought that up, Sarah.
But you are absolutely wrong.
That would be awareness.
Anybody remember what mr squared is equal to?
No.
No. Over B.
It's equal to moment of inertia.
Oh yeah. Yes.
So,
It's
another
like
way.
a fish swimming over a.
It's inertia fish.
So it's also equal to I alpha. All of these relationships with torque are also on your formula sheet. You want to make sure to look at that a couple times because torque is equal to so many different things that it's useful in a ton of scenarios. You really want to make sure you're fluent with how to use torque. And that's what this is all about. So that's just kind of a summary of some extra things with torque, and we'll get back into that later on.
I really can't think right now.
Yeah, I know.
Well, we got to power through this.
I
And
didn't calc back
It just
then.
randomly.
final questions on this?
No.
I don't have a question. I just don't know how this works.
Well,
Acceleration.
so torque
What is fish equal to?
is equal to this.
Angular acceleration.
Yeah, our fish.
I know R F is MA.
Yeah,
And how do you get the MR alpha?
because R and R is R squared. So you could rewrite it as,
How do you get R alpha?
because A is equal to R alpha.
Well, because
It's just an equation that we.
okay,
Yep.
so go first Thursday of notes where you have course. First thing we learned yet.
When you're thinking about going from something that's straight line to something that's circular, basically what you do each and every time is you multiply it by radius. Whether it's angular velocity, angular acceleration, whether it's torque, whether it's angular momentum, which we're going to get into, you take the straight line version of that equation and you multiply it by whatever the radius is. Speaking of angular momentum, that's where we're going next.
I'm excited for it.
So, angular momentum is coming next here. In the same way that we multiply r by our straight line equations in order to get their rotational equivalence, we do the same thing for angular momentum. Remember, momentum is equal to mv. So if I want to do a rotational equivalent of this, what we label it as, for some reason, is capital L. This is angular momentum. And that's equal to radius times regular momentum.
I thought P was.
It is.
But what's Ellison?
L is angular momentum.
Oh, okay.
Yep. So you can rewrite this as RMV. Another way of rewriting this would be R times, or just I omega, actually. So it's like, I know, right? Where does this come from? So here's the thing. I could go through the derivation, but that's a waste of time. So I is equal to mr squared. Omega is equal to V over R.
Oh, is the R.
Yeah. So the R's would go away. You've got MRV, which is the same thing as this. Therefore, they are equivalent. So, in the same way that torque is equal to different things, angular momentum is equal to different things as well. Now, maybe this is not something where you're moving in a two-dimensional plane. Maybe you have to deal with something that's, instead of at a right angle, maybe you've got some sort of angle that you're taking with respect to the angular momentum. So then it would just be Angular momentum times the sine of whatever the angle is. It's always going to be the force or the momentum that's acting perpendicular to the direction of the motion. So this is just the same thing that we did for torque. We're taking the component of this momentum here that's acting perpendicular to the object's motion. Of course, another way to say this is just your angular momentum vector is equal to radius vector cross momentum vector. And that's just your vector product, kind of like what we did, I forget how many days ago that was. But I want you to visualize this here. Go ahead and draw this. Yeah.
It's a really clean drawing.
Thank you.
Yeah, it's very visually appealing.
Good.
It's so straight. It's really happy.
And you know, that was the first time I drew it. I didn't change anything.
Like it almost looks like there's shadows
It's so
to it.
round.
It's so round and so straight, and it almost looks like there are shadows, and it's just really good.
You guys are going to send me into the weekend with a big head. Thank you.
That's okay. You can have a big head sometimes.
Sounds good.
Mine looks like an egg.
That's just fun. Eggs are healthy.
It's an egg that landed on the sidewalk. I'm not wrong.
Yeah, it looks more like that.
It looks like a Play-Doh egg.
Okay, so let's just briefly talk about this. In the same way that torque has a direction, angular momentum has a direction too. So this is like a plate that is angled kind of like this. So if you've got something that's going in a circle and its overall momentum at this point in time would be directed this way, then you could figure out the direction of the angular momentum by doing, guess what?
The right hand.
The right-hand rule. So,
Yes, the lighter rule.
the what rule?
The
lighter
rule. I thought you meant lighter rule. I don't know what the right hand rule is.
It's just right hand.
So yeah, you'd just take your hand and you would twist in the direction of the plate, and if it's angled, like this, you're twisting this way, causing this L to come up, and it would come out a little bit for being specific. So yeah, right hand rule to figure out the direction of the angular momentum vector.
Whoever invented this rule should have been recommended. It was recording. And more practical. The left goes clockwise instead of counterclockwise.
Okay. The other thing you need to write down, and this is a really important rule here. So, again, I could spend 30 minutes deriving this, but I'm not going to do that.
Thank you.
I'm just not. I'd rather do drawings that you're going to gush over than... So I said drugs.
Whoa.
I'd rather do
Let's go back to
drawings.
drawings. Let's go back to
Drugs.
I heard drugs, and I was like, what?
Mr. Mason.
Mr. Hathaway would never, ever do drugs.
Yeah, no.
Okay.
Hello, future.
On video.
Hi, Kylie.
In the future, it is found that cigarettes are healthy.
No.
That's
I'm
correct.
kidding.
I'm just kidding. No.
Okay.
Yeah.
If I knew how to edit, maybe I would. So, there's a relationship between torque and angular momentum that we must be aware of.
The video of Mr. Hadley. Cigarettes are healthy.
I want to see a video where Mr. Hathaway has a conversation with himself from the video. Yes! That'll be my.
I love this class.
Oh my God. See, and you even take it from different classes. So it's
Not
like,
really.
you could even line up when he was like wearing the same shirt on different days. Oh. Ooh.
Derivative
Ooh.
of
That would make me so happy.
in respect to pi.
Stop.
Backwards J with a squiggly line equals.
Mm-hmm. So occasionally you'll find scenarios where you have your angular momentum equation, and the only way to go any further is by using a torque relationship and to take its derivative. Like maybe you know a little bit about torque, you can set that equal to the derivative of angular momentum and find your way to the answer. You guys just love this, don't you?
I love it.
Is it the drug thing?
Yeah, you turn around and all of a sudden he's like, you flop his legs right.
Oh dear. What is happening?
You turn around like right in the face. What is happening?
I don't know.
My brain has done too much. Also, your comparative origins failed my biology brain today because all I wanted to do.
I didn't turn it on.
It was too like I was like.
Draw this. I command it.
Alright.
We gotta draw things again?
Yes, you do.
Wiggling for homophones. You grow us full your cheeks. It's so weird, but it's also like, what else would you expect? I know it's a stereotype. It's another really straight and beautiful drawing. Wait, so is this in relationship to that drawing?
No, this is different.
Okay. Because it determines if I go horizontal or vertical with my nose. It's like, I feel like there's some meme. I don't know which one.
There is no me.
But it's like, where there's one version of it, and then there's the representation of it, and it's really bad. I mean, a version of it is like the Winnie the Pooh one.
What?
You know, where there's one version, like there's the really ugly one, and then there's like the classic, and then there's the one with the serious. And that's how I feel like Mrs. Way versus my drawings. That's how I feel. I understand you. Huh?
The three-headed dragon one?
They do with a whole bunch of people. There's the one with
Yeah,
the
the
person in the
three-headed
orange coat. Who is that?
There's like the really cool looking one, the one that's
Oh, no,
got
that's a
the
different
eyes,
one.
and there's the cartoon.
Oh, maybe, yeah. There's a bunch of different versions. The first one I thought it was the first one. Yeah.
All right, so I would like to briefly talk about this beautiful picture here.
Very aggressive.
So, let's say... All right, eyes up here, folks. So, first, just focus on what's red. That's this one right here. Don't think about anything else. Imagine, if you will, that all you have is this mass, and it has a certain velocity in this direction. Now, if that's all you see, you might think, hey, there's nothing I could do with rotational motion with this. But your book would beg to differ. Basically, I'm only mentioning this briefly. The book basically says that you can have rotational angular momentum anywhere, even if you're moving in a straight line, because you could theoretically say that this mass is a certain radius from an origin point, and perhaps it's just that tangential velocity of a larger circle that it's doing. So, all I want to say about that is whatever. And the other thing I want to say is, if this was moving in a circle, what direction would the angular momentum vector be going? At you, exactly. Because you curl those beautiful right-hand fingers along with the direction of the motion, your thumb points outward, and that is the direction of your angular momentum for this one. That's all I really care to say about that. Questions on this?
Good circle.
Thank you. And I've got one more picture. Boy,
Yeah!
I have
Watching me really, really bad.
I
would
really
die.
hope this doesn't disappoint you guys. All right.
Now comment on this one.
What do you think? Be honest.
Alright.
Okay, the
It's
one
very
circle
strange.
is a little
Pleasing to
wonky,
me how the
but
line
it's-
coming from M2 to
but it's
connecting to
also
M1
satisfying.
goes along the red line. I think that's visually
And
appealing.
the corner of the square.
Yeah,
This
that
is
is all.
pleasing.
Okay.
Because it's a bigger top.
No, but that adds
But
depth.
it-
That
Yeah,
adds depth.
exactly. No, I like it.
Perfectly in the corner.
Does it capture
Would you
the...
stick a pulley exactly on the corner?
Yes.
Yes.
Yeah.
My only question is, does it capture the essence of Newton's laws?
Yes.
Okay.
Oh, 100%. I don't think of anything
I
else.
think it's exquisite enough to the point
But-
where at this point it's halfway.
So the
across.
red circle is a little wonky, but then the green line goes so nicely on
I
it.
mean, it really does.
Like
holds
it's
it together.
perfectly.
Like it has to be wonky.
Boom.
And otherwise it would be messed up.
You had a really good day for drawing, Mr. Raphael.
Thank you.
We gotta give it to you.
I appreciate
And
that.
that curvy arrow over there,
Oh,
it's aesthetically pleasing.
Which
it
curvy
gets
arrow?
thinner
Over
and
here?
it goes
Yeah.
back out. Ooh.
All the way on the right.
The one thing I'm most impressed with is kept the same like width.
Oh yeah.
Oh,
Yeah.
and the word moment, I just looked at it, and it's really good.
Thank you.
Okay,
Yeah.
question.
It's so good.
And it's
Are we
top
doing
guys.
any examples with this?
Every day should be this
Is
day. What?
this a problem?
Yeah, draw this.
But is it an example or is this just...
This is a problem that we're going to be solving.
And already my line is.
Because I have that awkward amount of space left and I'm trying to figure out if I should...
It's really not that long of a. It's medium length.
Okay.
I would probably say you could get through it in 9 lines.
I'm gonna be completely honest. I have 8 lines left. I'm serious. Oh, wait. I wrote this all on the wrong page. I wrote this in the middle of a different note. Dang it.
Oh,
I don't know why. I saw
no.
one
Look at
page
how we
instead-
compare.
No, I wrote it. I was like, why do I have stuff on the next page? This is like when you're in 3rd grade, you just pick a new page to write on every day. It doesn't have to go in order.
Yeah.
Yes!
Dang it, Mr. Halfway now.
After remembering 3rd grade.
Yeah, sure is.
I don't know how I didn't notice that the stuff I wrote above it had nothing to do with anything.
My picture is a mess.
And that's okay.
And so, yeah, by the way, you always put your pulley on the very corner. I don't know if you guys are talking about.
I think Mr. Hathaway was just trying to open our eyes to a more realistic.
It's okay if Mr. Halfway does it. Mr.
Exactly.
Halfway would really,
Or it was supposed to be more realistic. You were like triangle.
No, stop.
My style is ahead of its time. It's okay if you don't understand.
that's fair.
What are we doing today?
It's moving. You know, just pull...
Guys, we don't have to go to school tomorrow.
Guys, we have a calc
Yeah,
class
what are we
tomorrow.
doing tomorrow? Are we-
Yes, but no for me.
Just keep an eye on Schoology. I'll post something short for you.
Can I
Can it
just
just be
feel
like a
like,
check-in
what's
here?
your favorite color?
Jay,
We'll
explain
see.
me your mental state.
I'll come up with something. Maybe I don't
We
know.
should
I'll
all
think
have
of
to
something.
submit a dad joke.
That's not a bad
that's
idea.
A good one. Oh,
Hmm.
What's black, white, red?
Oh, I have Laffy Taffy, so I can just go whoop and
What's
then.
black,
I
and
can
white,
just
black,
go-
and white, and black, and white, and
I
black.
can just go whoop. Also, I would like to.
Did you find one?
I don't know. Probably.
Okay,
Potter, what's black and white and black and white,
Yes,
black and
they
white,
are.
black and white, black and white, huh?
so we need to tackle this problem. Here is our setup. We've got mass 2 on top. We've got mass 1 that's hanging. And mass 1 is heavy enough that it's pulling mass 2 across the table to the left with a certain velocity. This is a pulley here. R represents the radius of the pulley. So when you see R in the equations that we use, it's just that little radius there. And I stands for the moment of inertia of the pulley. That's something we have to take into consideration now. Because we've done questions like this in regular physics with, Newton's laws, but realistically, now that we're in super advanced physics, not only do we have to take these masses into account, but we got to take into account the fact that this pulley has a certain mass to it, and it's going to take a certain amount of effort to get it moving and get it stopping. And so we have to take a look at that and make sure that we're being complete in our analysis. So, let's do this. The ultimate goal here is to figure out what the acceleration is of that system, which we could do if we didn't have to deal with the pulley itself. So,
Just cut it off or like break it off the wall.
if we can replace it with a frictionless thing there, then yes.
Okay, we're perfect.
And can we?
I guess
No.
it's a torque.
So this is our angular momentum up there. When you figure out your overall angular momentum, you have to add up the angular momentum of everything in the system. So this would be mass 1, mass 2, and the angular momentum of the pulley. We have to take all of those into account.
Wait, mass 1, mass 2, what?
I don't know, man. Just copy it until you understand.
That's how I get through this class. Just do enough examples and you'll be fine.
After 3 days of not understanding, I usually catch up at some point.
Yeah, we'll hit that point eventually.
No, I'm dead serious. I normally understand a day or two before the test.
It's all of a sudden
It
it
all
clicks.
just clicks.
Yeah.
Like, I'm decent, and it's like, oh, I know how to do this.
So because we have this pulley here that's spinning in a circle, and it's interacting with mass 2 and mass 1, those masses have some form of angular momentum.
Gotcha.
So another way to say it is RMV.
So, how do you get IW equals IW? Because IW equals IW. Here's what inserted in. IW equals
Now remember, I omega is another way to write angular momentum. That's why I'm putting it here. The pulley itself is not moving with a certain, straight line velocity like the masses are. So I have to take angular velocity into account for that pulley. And remember, another way to write angular velocity is V over R. And this all has a purpose to it. So that's about as far as we can go in terms of the angular momentum of the system. Questions on where any of this came from? Yes.
Okay, so P is momentum, right?
Yes.
Okay, so I was just confused because it looks like a lowercase p as opposed to uppercase p.
Yeah, lowercase p is momentum. Uppercase p would be power. So that's as far as we can go with angular momentum. So we have to look somewhere else, and usually that somewhere else ends up being torque. So let's see what's going on with torque. There is only one mass that is providing torque here, and it is M1, because it's actually doing the pulling on the pulley system. It's going straight down. So torque is just equal to radius times the amount of force. Radius times force of gravity 1, I'll say. So R M1G. Questions on why that is? Now, torque is also equal to the derivative of angular momentum. I wonder what use that is going to have here. We're going to find out soon. Anybody have a guess? Remember, we're solving for acceleration.
Then help us find
Then
acceleration.
you just go R
The
and
derivative of torque is acceleration.
It's R.
You set the derivative of torque.
Well, because we have velocity in our equation.
Wait, why are we raising all this?
Oh, you weren't done writing?
No, I'm done.
Oh, okay.
Wondering why.
We got to switch to a different color. What color should I use?
Black.
Blue.
I'm out of black. I do have blue, though. Let's do blue.
Was that the only one?
Why did you
You
scroll?
all
We have
of the green.
velocity, so we can't
Wasn't it just
technically
green,
get acceleration from that.
So,
Seems like a Mandela.
torque is equal to derivative of angular momentum. And torque we found is equal to radius times mg. And we can set that equal to the derivative of our angular momentum expression. There's r mv plus r mv plus I times v over r, if I remember right.
What?
Right?
Yeah.
Okay. This is from when we were looking at angular momentum. This is how we ended
Yeah,
that.
look at it now.
Can't we factor out those velocity?
Well, we could, but we don't want to do that just yet.
Okie dokie.
Does V stand for velocity?
Oh,
That's supposed to be a T.
that's a T.
Yeah.
Yep. So, remember, we treat everything over here as a constant unless it actually changes with respect to time. What's changing with respect to time?
Torque.
Correct.
Torque. Not torque. I don't know.
Do it again, Katie.
Velocity.
Velocity! Exactly.
Yeah,
If you take the derivative of velocity, what do you get?
Acceleration.
Yeah.
That's what I said
Yep.
Sarah said
Sarah was right on the money. I didn't want to give it away too soon, though.
Oh, I said velocity. I don't know.
So, that's where we're at. And look at all those A's.
Look at all those.
It's like looking at your old regular physics tests, right?
Oh.
So,
I don't remember. It's too long
we're
ago.
trying to, gosh, I remember last year, everybody was always like, I am so going to fail this test. And it's like class average, 93. Pretty much the same this year. You guys are doing very well on your tests.
Except for you, which is me.
You know, this last test was my best test.
Yeah.
This was my worst test.
Very proud.
Well, that's
This
because we're
is
here
one
for
of
review.
my lower ones.
No,
Oh, actually.
and because
What is the test?
what did you go? I'm not a good student.
What test?
Did you cheat?
All right.
I figured it
I
out.
got a 1.
So we've got this.
I've only seen so much. I'm like, are you just writing it again?
Therefore, if I want to solve for my acceleration, I am just going to yank it out of there. And I do that by dividing both sides by this thing.
What thing?
This thing.
Yes.
But why would they put that equal to a variable hole? At least in reality, just to mess with people's minds. Make that equal to like.
You have to make A equal to B, but
Should
then
we
C
put that
and B.
R on top from that I?
Well, I mean, you'd have to, because it's just over here. You can't just throw it up here unless it was in the rest of these. But
Ha ha.
so yeah, that's how you get acceleration. And you know, this was a big long procedure that you're probably not going to remember over the weekend, and that's okay. The main thing you need to remember is that there's a relationship between torque and angular momentum. And you have to always be aware of that relationship because it can help you solve a lot of the problems in this chapter. You have to know your torque and you have to know your angular momentum
Like,
and the
what are
relationships
some,
between
like,
them.
Real life examples that we can actually use this.
Well, this is a real life example.
Get done.
Anything that's spinning, anything that's moving, you got to actually take the moment of inertia of the pulley itself into account if you want to get an accurate result. One of the classes, if you would continue on in college, is called Analytical Mechanics in Physics. And basically what you're doing is you're taking the stuff you learned here and you're adding everything else you need to add in order to get those numbers to be perfectly accurate in the real world. Like the stuff we do in regular physics probably gets it about 90% accurate. In this class, brings it to about 98% accurate. But to make up that last 2%, to make sure you're doing friction just right and you're doing air resistance just right, there's a few other things you need to take into account to make it apply exactly to the real world.
That's where the super smart computer comes.
There you go.
If you never
All right.
need it.
Any last questions? All right.
Bye. Bye, Kylie.